Welcome back. As you know, I am Eli, the computer guy, and in today's class, we're going to be talking about push-pull communication and polling within systems architecture. So what are we talking about when I say push-pull communications and polling within systems architecture? One of the big things that you need to be thinking about when you start building out your architecture and your infrastructure is basically how all of your devices and systems are going to be able to communicate with each other. So back in the day, not that long ago, more or less everything was within your premises, right? Your servers were within your premises, your computers were within your premises, your VoIP, voice over IP systems, your surveillance cameras, your access control systems, all of that kind of stuff was completely and utterly in your premises. So communication amongst all of these devices was relatively easy, reliable, and fast. Even when companies started going up to the cloud and they started putting their systems up in the cloud, most of those systems resided in their own data centers. Either a company would choose a single vendor, such as Microsoft Azure or AWS, to host the services, or they would go to a co-location facility, something like that. So even though the servers were up on the internet, from a communication standpoint, they were more or less sitting side by side, and they could communicate really quickly and again reliably. The problem we run into in this modern world, though, is again we're going to this whole architecture of service-oriented architecture. Well, now actually we're going to microservices architecture and I don't know, there's a whole bunch of architectures out there, but we'll just stay with the whole concept of SOA because I think that's like the granddaddy of all this, and so it's easiest to understand. And so basically with service-oriented architecture, what we have is a whole bunch of services spread all over the damn place, and basically your devices, your computers, your servers, your host systems have to be able to communicate, receive communications, send communications, be able to do something with all this this data that's going back and forth. And so in this world, we need to start thinking about how these devices actually communicate with each other. Again, if you have a host computer and a server in an Active Directory network, and it's on your local LAN with a gigabit switch, you're not really thinking about how these devices are communicating with each other, how email is getting sent back and forth, how system alerts are popping up, those kind of things. You just sit down, you tippy tap type on your keyboard, and the communication is occurring. The thing is, once we start dealing with this IoT, so Internet of Things world, the service-oriented architecture world, we start to have divergent devices, divergent services, all kinds of stuff all over the place. And with that, the reliability of the network may be better or worse. The speed of the network might be better or worse. The resources for whatever servers or services are providing the services to the end user may be better or worse. And so we start to have to think about the actual communication between devices and servers, or devices and other devices, and that type of thing. And so when we talk about push and pull, so basically there's push communication and there's pull communication. This is pretty simple. Push communication is when one system sends data to another system. It is pushing the data to the other system, right? And that's pretty simple. Pull communication is basically when one system reaches out, communicates with another computer, and then has the data come back to them. So think about this with the old POP3 email or IMAP email. Bro, POP3. Do any of you remember POP3? Sometimes it gets really hard to start talking about technology topics when you realize things have become obsolete and old. Anyways, with POP3, you would have your email servers up on the internet. You would have your client computer. Basically, this was a pull communication style. Your client computer would communicate with whatever the POP3 email server was, and then basically pull down all of your emails. Your emails would not come to your client computer until you went through this pull process. And so this is something you need to be thinking about, right? And again, we talk about this with IoT. So we're going to start doing more IoT projects for the classes on the main Eli, the Computer Guy channel. And with IoT projects, basically you've got all these devices And you have to start thinking about how they're going to be communicating, especially on low bandwidth modems. So I have a Blues IoT modem that's actually really cool. And one of the things to be thinking about it's only got 500 megs of total bandwidth over 10 years that it can use. The speed is very, very, very low. Basically, it can only send a JSON. And so one of the things to be thinking about is how is that kind of device going to be sending information? Or how is that device going to be receiving information in a way that the system functions and things kind of don't go to hell, all right? This is what we're talking about with push or pull communication. What polling is, so polling is Polling, is basically the process for poll communication where your computer communicates with the server to ask for any new data. Hey, do you have any new data? 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 It's polling. So it's doing a poll, P-O-L-L, before it does a pull, P-A-U-L-L, to pull the information down. Now, one of the big things that you need to be thinking about when you think about this whole concept of push or pull communication is whether you're having to deal with NAT. So NAT is something called network address translation. So this is a thing, became really popular, I don't know, back about 99, 2000. And basically what this allows you to do is it allows you to share your external IP address with any number of clients on your internal network. So if you have 100 users on your internal network and they're able to get out to the internet through one ISP connection, they're using NAT. This is called network address translation. So basically you have your router that goes out to the cloud. You have the different computers in here. When this computer wants to go to CNN.com, that gets routed through the router on its external IP address, goes out, gets the information for CNN.com, it comes back. The router basically keeps track of who's going where, and then it automatically routes CNN.com back to the appropriate user. A different user is going to Fox.com, because we've got to be fair and balanced anymore whenever we do anything. Somebody else goes to Fox.com, it goes out, and then the traffic gets relayed back to the user that was going to Fox.com. The problem is that we get into this is TCP ports, right? So transmission control protocol ports, when we talk about TCP IP version 4, TCP, one of the things in there is ports. This is where you hear about port 80, port 25, port 21, port 22, SSH is 22, HTTP is 80, what SSL is 443 as I recall, a whole bunch of numbers. Well, here's the thing. Here's the issue, right? So if I have one computer here, and I have one computer here, and they're on the same network, they're not going through the cloud or anything like that. Basically, they're able to talk to each other on whatever port they want to talk on. So if this one wants to talk on port 80 for communication, this will return the communication on port 80. If I want to talk on port 22, it'll return communication on port 22, right? The TCP ports on that local area network, unless you have firewalls and other horse crap set up, we're not going into that right now, will work fine. The problem is when you're dealing with NAT, the network address translation world, what happens if somebody out here in the internet wants to come to this external IP address and then wants to get to a particular port number on a particular computer in your network, right? So this is 192.168.1.50. This is 192.168.1.25, so on and so forth. And so what happens if somebody here wants to get to 192.168.1.50, port 80, the HTTP port for basically being a web server, and they want to do it from the outside world, right? So NAT is all about going out. That's all about going out. You do communication through your router that has NAT. Your router keeps track of that communication so that the response that comes back to the appropriate host computer. The thing is, when people are in the outside world trying to communicate into the network, right, NAT doesn't work out so well, and that's why we have something called port forwarding. Right? And so what port forwarding does is basically within the router, it'll say, send all port 80 traffic to 192.168.1.50 or .1.25 or .1.60 or .1. Whatever else. Here's the thing. again, more or less depending upon your networking equipment, you can only do this for one host. So port 80 can only go to 192.168.1.50. Port 22, if you set it up, will only go to 192.168.1.10. Port 25, is that FTP? Anyways, one of those will only go to 192.168.1.105 or something. The issue that you get into is what if you have multiple servers that are basically running web servers, Apache or Nginx, and you want them to be interacted with from computers in the outside world, right? You think about this communication style. And so that's one of the issues that you run into with communication is if you have anything on the outside world trying to communicate into your network, it becomes just a disaster with trying to figure out things like port forwarding and all that kind of stuff, especially if you have a large network. And so that's why things like push-pull communication become important, because as you start to think about your devices, and you start to think about your servers, and you start to think about how the communication architecture should work, you then have to start designing for that, all right? So if I have a server out here, and it's on the cloud, and I have my low router, and I have all my devices here, right? So what happens if this computer here needs to get information from this server? So what is push? Push communication would be for this server to be able to push down to the external IP address sitting on this router that would then forward the information to this particular host, right? And again, when I talk about a host, we have to think about the modern world. A host is not necessarily a Windows 10 computer, a Mac computer, or an Ubuntu computer. It may be a Raspberry Pi. It may be an Arduino. It may be an ESP, whatever the hell, 8266s or whatever the hell they're called, right? And you may have lots and lots and lots of them. Like what happens if you have this server here and it needs to communicate with this device, 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 right? Well, you get port forwarding, right? You can only forward to one internal IP address. So if you try to do push communication from this server to the local devices, it's not going to work out so well. It's just not going to be a good thing. And so what do? You set up these devices to do pull communication. So basically up here on the server, this server has JSON or whatever data type you want them to pull. And then what happens is your devices will then go out to the internet, it'll go to the server, it'll pull down the JSON. It'll do a pull. It'll say, hey, I need information. The server will create the JSON value and send the JSON value back as a pull. This device does the same. Hey, I need information. It will send back the JSON value as a pull. This device is the same. Send back the JSON value as a pull. This device is the same. It'll send back the JSON value as a pull. So therefore, you have all of these devices now. All of these devices are able to now be updated by this computer or this server that is up on the internet, because now they're doing pull communication versus push communication. And so this is something to be thinking about. Now, when you sit here and you think about it, though, again, we start talking about architecture and infrastructure, service-oriented architecture, microservices architecture. And basically, in this kind of world, you know, every single computer, instance, whatever the hell you have going on, is providing a particular service, right? So this is kind of some kind of command and control. But this might be getting information from some kind of database type server or some kind of other server that is pulling in information. So let's say you have some kind of server that's doing parsing, and so it's parsing information from REST APIs, right? So it's going out and it's looking for weather. It's going out, it's looking for alerts. It's going out and it's looking for different information, right? So it's going out to a number of different REST APIs. It's saying, what is the current weather of this area? What are the emergency alerts of this area? What is the news of this area? Whatever else, it's pulling, because this is actually pull, right? It's going out, it's asking, so it gets the information pulled back. And then it brings it in and it parses it and turns that information into something that's useful. Now, once it has that, right, so it's constantly going out there and it's constantly scanning. Since this is on the internet and it's IP addressable, so it has an internet routable IP address. So these are internal IP addresses, 192.168, 10.1, whatever else. These our internet routable IP address. It has an internet routable IP address. In this situation, right, this computer that's parsing all of this information can continuously be parsing this information, and then whenever there's a change, whenever there's an update, it can simply send out, it can do a push notification to this other command and control server to state that there has been an update, and so this server should now start sending out that update versus whatever its previous data was before, right? So these two systems are able to see each other because they have internet addressable IP addresses, or possibly they're within their own cloud infrastructure or whatever else. Since they're able to see each other, then the parsing server is able to send only whenever there's new updates that need to be sent, and then all of these devices are then able to pull from that server as need be. One of the reasons that you do this then is it lowers the resources, right? So basically this computer, this server is constantly pulling information, constantly scanning information, and then when there is a change, and only when there is a change, does it push the data, right? So that means overall network communication between this device, this server, and this server is relatively low, right? Update happens, send update, that's it. One of the things you need to be thinking about with poll communication is polling, P-O-L-L-I-N-G. So again, with this, nothing magically happens. Nothing magically happens in the technology world. So for these devices, periodically, they have to make a poll request from the server. Now, one of the things you have to be thinking about is how often do you want to make that poll request? Should every device on your network make that poll request every second? Every 60 seconds, every hour, every day? What is the right answer? Who the hell knows? That's one of the things you have to decide as a system architect. But what you have to be thinking about is whatever this timing is, all of these devices at that timing are going to hammer the server. So if you have 10 devices on your network, you have 10 IoT devices on your network, and they are polling this command and control server every second, that means 10 devices every second are going to be communicating with this command and control server, and you're going to have that load. Now imagine 50 devices every second. Now imagine 100 devices every second. Now imagine 1,000 devices every second. Now imagine 10,000 devices every second are making a request of the server, right? Think about how much more resource load there is versus on just a push notification where only when an update happens, then there will be communication. So these are going to be polling. They're going to be basically, whatever the schedule is, they're going to be making that communication call whenever that schedule is to ask for an update. If there is an update, they will pull that information down. But there is network resource utilization, not simply on pulling the information down, but simply on making that request. And that's one of the things that you have to consider with this whole kind of push-pull architecture and how you're going to be setting things up. So when we're thinking about the considerations of creating this kind of push-pull architecture, whether you're going to be using push, whether you're going to be using pull, one of the things we need to be thinking about is timing. Again, how often is a push request, basically polling, going to occur, or a poll request going to happen, right? So if you have two servers here, basically how often is one server going to communicate to the other if you're doing something like a push request? So this is communicating out with all those REST APIs. It's gathering the information. How often is it going to be sending that information to this particular server? One of the things you need to be thinking about, again, even if this is on its own infrastructure with its own IP addresses, you may be having multiple servers that all need to send data back to this one server. And so one of the things that you just want to consider when you're setting up your infrastructure is making sure this one server doesn't get overloaded with communication, right? So these they're all pushing their data to this particular server. Does something get locked up? Is there enough bandwidth? Are there enough resources in the server to be able to deal with all of the communication coming in? And so that's when things change on any one particular server. You may simply have it set up is regardless of how many changes happen, only push out data every 60 seconds. Regardless of how many changes happen, only push out data every 10 minutes. Or, again, you may have it so every time there is a change in data, that data is sent out immediately because the communication is fast enough. But one of the things you need to be thinking about is basically how many devices are going to be pushing to that one particular server, and are there any kind of resource constraints? Are there any kind of like wackadoodle things, anything that might lock up the system and freeze things up if you have all of these devices trying to push communication at the exact same time? That's something to consider. And then when we start looking at pull really becomes more important. So push generally you can push in near real time. Again, as soon as updates happen, you can generally push. But one of the things you do need to be thinking about is, again, with that server up on the cloud, you got your router, you have all of these devices here. One of the big things to be thinking about is basically how often are they going to be making those pull requests? Again, especially depending on how many devices you have. If you have 10, it probably doesn't matter. If you have 1,000, it really starts to matter. If you have 10,000, you better figure this crap out, right? Right? Again, remember, it's load. So many things in the technology world, that's one thing that really screws new people up, is they deploy something that has one client and it works magnificently, and they think that's fine. And you're like, well, that's one client. How's it going to work with 100 clients or 1,000 clients? And so that's one thing, again, with this whole polling process, where each one of these devices are going to be going up and communicating with the server on the internet. You need to be thinking about things like bandwidth constraints. Again, normally when we think about modems, we think about, DSL modems, cable modems, fiber optic lines, that kind of thing. You may have some kind of cell modem system here, right? So you could actually connect a cellular modem to your router, and that cellular modem basically has 2G connection, which is about 56, K kilobits per second speed. All right. Now imagine if you have 1,000 devices all trying to communicate through a 56 kilobit per second connection speed. That might cause a problem. Now again, one of the things you have to think about is how you design the system. Probably not, but 56K might be okay if this polling rate is pretty low. If each of these devices only checks for new data every 30 minutes. And they're all on a randomized schedule, so they're not doing it at the same time. Again, if you set them up to only do it for every 30 minutes, but all of them do it at the exact same time mark, it's still going to be a disaster, right? But if this one does it at 10 o'clock in 1 second, this one does it at 10 o'clock in 2 seconds, this one does it at 10 o'clock in 3 seconds, right? You space it a little bit. That might actually be enough, so all of these communications are occurring even over this relatively low speed connection. It's one of those kind of things to be thinking about. But one of the things you have to be thinking about, though, is with that scheduling, it means that your system will only update every 30 minutes. So one of the things I want to create using the little Blues IoT modem I just got is kind of like an alert system for delivery vehicles. So one of the things I've been thinking about is in this modern world, so many delivery companies, installation companies, that type of deal, basically are using AT&T and Verizon and those types of systems. The issue is that costs a lot of money. You don't really own your data. People are tracking you, the whole 9 yards. So one of the interesting things, I had the idea, is using this little Blues modem, basically connecting a screen to it, connecting a keyboard to it. It will be able to GPS track the vehicle as it's used throughout the day, but then you'll also be able to send messages to that device, and that device will be able to send messages back. The cool thing is that all that information can be stored into a database system so that it's all owned by the company, can be mined by the company. You can do all kinds of fancy things, right? But one of the things to be thinking about is what happens if there's like a weather event. So, you have installation crews, they're out in the field, they're doing whatever. You have a system, right? So we dealt with a REST API for national weather alerts before in a different class on the main channel. And so what if the National Weather Service says there's a major tornado coming through an area, and so you would want your people to know that information, right? So they send you information when they get to site, they send you information when they need new tools or whatever. You want to make sure that they get the alert that a storm is coming through. Well, here's something to think about. If your poll scheduling is every 30 minutes, that means if their device just made a request from your server, they're not going to get this alert for another 30 minutes, or 15 minutes, or 5 minutes, or 6 hours, whatever that schedule is. And so that's one of the things you have to think about when you're designing these systems is how do you balance resource consumption, that type of thing, and the needs of the people that you're trying to serve. So if a storm is coming through, an alert goes out, but half of your technicians do not realize a storm is coming through because the polling is the schedule for that is so infrequently, you're going to be running into some issues. So this is the kind of thing to be thinking about. The other thing to be thinking about when you think about push, pull, and scheduling and all that, and again with service-oriented architecture, microservices architecture, whatever fancy architecture we're talking about nowadays, is remember it's a bit of telephone, right? So you have your device here. You have your device that's communicating with this server. That server may be communicating with another server. That server may be communicating with a couple of other servers. So one of the things to be thinking about, when we think about computers, we think about information at the speed of light, right? That's true. You get packets at the speed of light. You definitely get packets at the speed of light. Whether or not you get information at the speed of light is another story, right? What if this thing only updates, let's say every 10 minutes, it makes its API calls. And what if this thing only updates every 10 minutes? And what if your thing updates every 5 minutes, right? You heard me, you heard the warning. Eli said, be careful, don't do the polling scheduling at 30 minutes because then your people might get run over by a tornado. So you're going to be smarter than that. You're going to make sure each one of your little IoT devices does polling every 5 minutes, right? So you're saying, that's fine. Every 5 minutes, your little device is going to go up and communicate with a server, and so it will have updated information every 5 minutes. Will it? If this server that's pulling information only queries every 10 minutes, and then this server only queries every 10 minutes, or now 20 minutes, and then your device queries every 5 minutes, you're now looking at a 25-minute lag time from when data is available from APIs, REST calls, whatever else, to when it actually gets to your device. And so this is one of the things that you have to be considering because yes, packets move at the speed of light. Data can be shockingly slow. Now, the next thing you need to be thinking about with the whole push-pull architecture, figuring out scheduling, all that kind of thing, is the actual hardware resources. Don't tell Node developers this, but hardware still matters. It's shocking to say, but not everything is actually made with code. Sometimes you actually have to have physical stuff. One of the issues you can run into, again, with this whole kind of push-pull architecture is people do not allocate enough resources for the servers that are providing whatever services, right? They go to Linode, they go to DigitalOcean, they get a $4 instance or droplet or whatever up there. They get a little Raspberry Pi, maybe a Raspberry Pi Zero that can run a database, and they think, yay, we're done. Just send the data or push the data, pull the data, we'll be okay. One of the things to be thinking about, though, again, whenever you're thinking about data, is again, what happens with these devices, right? So you have this computer. Let's say you have this server. And the server is either sending communications out or it's receiving communications. One of the things you need to be thinking about is when the communication comes in, what happens to that communication? Does it simply get written to a text file, TXT file? Probably not. Most likely, it's going to go into some kind of a database type system. So Postgres, MySQL, maybe SQLite. Have you used SQLite? I really like SQLite. Anyways, so one of the things to be thinking about as data is coming into this particular server, it actually, right, there's a SQL statement, there's an insert SQL statement, and that data has to be inserted into the server. Well, that's not too bad, right? Resource consumption on insert statements, you're probably doing pretty good. Now, here's an interesting thing, though, to be thinking about in this whole IoT world. When you have thousands and thousands and thousands of devices, and they're all just sending a metric crap ton of data. Because remember, Silicon Valley says data is the new oil, and Silicon Valley is never wrong, right? Here's the thing, right? You got thousands of devices, and they're all sending information to your crappy ass little Linode server. Fine. Who the hell cares? Well, here's the thing. There's going to be other devices, maybe these 1,000 devices, maybe 1,000 other devices, that are going to be doing polling, right? So these are pushing values. So these might be IoT sensors, God knows what. There's some kind of devices that are pushing data, again, sensor values, text information, or whatever else, into the server, and they are getting inserted. Then you have another 1,000 devices, or possibly these 1,000 devices, and they then need to be told what to do. Based off of these sensor values, do we turn on the HVAC? Based off of these sensor values, do we turn on an alarm? Do we turn on lights? Do we trigger, what kind of events are going to trigger? Are we going to send out emails and God knows what, right? Well, as soon as you start thinking about that polling, right, where these devices are going to be getting information, that's where we get into select statements. And so what a select statement is in SQL is basically you're just trying to get information out. So each one of these devices, it says, hey, I'm device A, select all select all in whatever table where device equals A. Well, now with a select statement, when you're inserting, you just insert and go. Insert and go, insert and go, insert and go. Jab, jab, go, jab, jab, go. When you're doing a select, you're getting in this mess because now that database has to go through that entire table and find every instance where the device is A. It has to then grab all that information, process that information somehow, and then send back whatever. Turn on a fan, turn on AC, whatever else. That's A. And then you have device B, C, D, E, F, G, off to infinity devices. And so if you have this on your crappy ass little Linode server, simply doing something like a select statement, if it's not properly written and you have this god-awful database structure, might actually bring your entire system to a standstill. So one of the things you need to be thinking about with this type of communication is what are the resources your server is going to need, and have you allocated resources appropriately, especially as more and more devices come online for whatever infrastructure that you're building. And so when you're thinking about this whole database communication, we go back to the last class we did for this particular channel to the concept of caching. Right? So every time your server has to make SQL statements against the database, especially if they're selects, especially if they have joins, especially when they have order bys and a whole bunch of other stuff, that takes an amount of resources. Again, if you have one client asking for crap, who the hell cares? Again, 100 clients might actually matter. 1,000 clients definitely matter, and 10,000 clients, you better figure out what the hell you're doing, right? Going and actually doing these SQL statements takes an amount of system resources. So one of the things to be thinking about, again, with this whole, let's say this pull request, right? So you have this client here, it's going to make a pull request, it's going to send the data back, is using some type of caching system. So instead of having your computers, whenever they make a request, actually having to do the SQL statement, you could actually have your system on a schedule, again, every 10 seconds, every minute, every 5 hours, whatever else. It could do the SQL statement on its own and essentially output that information to something on the order of a text file, or maybe it's in another table within your database, but just simply has the results. So all there is the results. So basically, you do the statement, you get the results, you figure out what's supposed to happen with the results so you can give the command, and then all of that information again is put into a text document or possibly put into its own specific table, so that when the client computer requests the information, instead of doing the SQL statement, it just goes to this cache that has been periodically created. The value for this is then you can schedule resource consumption. So basically you can simply create a loop, and basically that loop will go through, and for every device that's going to communicate with a server, just simply create a cache file, create a cache file, create a cache file, create a cache file, create a cache file. See, the nice part about that is then you don't have 1,000 devices all trying to do SQL statements at the exact same time. You do this SQL statement, cache it, this SQL statement, cache it, this SQL statement, cache it, this SQL statement, cache it. Those devices are now grabbing that cached information and grabbing simple text information. Who the hell cares? There's very low resource consumption on that. And so this can make it easier for things like allocating resources and basically making sure that your server doesn't crash under a particular load. So that's one of the things. Again, we talked about caching before, and that might be a good thing for setting up your particular system. Now, one of the final things to be thinking about with this whole concept of push, pull, architecture, and polling is the idea of acknowledgements. How do you make sure the other side got the data and stored it appropriately? I think about this right now, so I'm creating this whole weird AI communication system. So in the main channel, I'm doing this whole series where I'm showing how to create like an AI system that you can talk to in natural human language. So with that system, basically there's a whole bunch of functions: get weather, get time, say hello, tell a joke, all of that kind of stuff. And basically using OpenAI, one of the things I'm able to do is you're able to talk in just natural human speech. It's able to figure out the appropriate function, and then it fires off. It tells you say que hora es, and it will tell you what the time is. You say el tiempo, it will tell you what the weather is. You say bonjour, it'll say hello, and I don't have to hard code that crap. One of the things I've been doing is with that system, I've been adding both a caching function and also a learning subsystem, so that if OpenAI doesn't know their appropriate response, I can actually teach it. So if I say, I don't know, Bubba over midnight, God knows, I say something, right? And OpenAI doesn't know what I'm talking about. I can say that means what time is it? Or that means what is the temperature, right? And so the cool part about this is it caches. Whenever there's a request to OpenAI, it caches what the request was and what the response was, so that if that same request occurs again in the future, instead of going out to OpenAI, it'll just use that local cache. And also, if OpenAI comes back with an "I don't understand," you can actually say that means, right? And so it's this whole system where OpenAI is taking a heavy load for being able to do the natural human language understanding. But there's this subsystem to both cache responses from the past, so we don't have to keep making those API calls if people make the exact same request, and has this whole little learning function built in. Well, anyways, I was going through and I was playing with it, and it was working great. And I was teaching it all kinds of weird naughty words. Naughty words! Because yeah, no matter how old you get, it's always funny to make computers say naughty words. Anyways, and I was running into this problem where while I had the script open, it learned the information, I closed the script, I reopened the script, and it forgot everything. It forgot everything. And do you know why it forgot everything? Because I forgot to do a commit. Whenever you're using SQLite in Python, you have to do connection or con or whatever .commit function in order to actually, it's this weird thing like, when you're using SQLite, you can use the commands, but it's all temporary until you commit it. So if you don't commit it, then when the script stops, it all goes away, which is kind of interesting from a security and other kind of problem. But if you forget to commit and you want to commit, it's a bit of a problem. So one of the issues you need to be thinking about, again, with push, pull, and polling communication, this actually does make sense. So you have, your server up here, you have your devices, or you have your multiple servers. One of the things you need to be thinking about is some kind of acknowledgement to make sure that your devices are actually getting the information that they're supposed to get, right? So think about this. If we do pull communication, so this device A, communicates up with the server then sends data back, and is that it? Is that it? What if there's an internet problem? So that communication going back doesn't get there. What if the coder was a dumbass and forgot to put the commit function in? So even though device technically gets the information, doesn't get stored how it's supposed to get stored. What if the power goes out? What if the power goes out? So this device just drops off the network, right? If you don't have some kind of acknowledgement system, this server will log that A communicated with me at this time period. I sent to A this information at this time period, and everything's good. Right? That can be a problem. Or again, if you're sending, let's say you have temperature devices, right? It's saying 99 degrees. So this device is sending 99 degrees. The command and control server looks, goes, oh my God, 99 degrees is way too hot. So it sends turn AC on. Well, here's the thing. Again, and think about this in the real world, because again, you got users at the end of the day. At the end of the day, you've got users. At the end of the day, you have some poor bastard sitting down at the console trying to figure out what the hell's going on. And now, in a remote world, it's not like they can walk to the server room and see what's going on. This may be, a couple thousand miles away. And so, if this sends 99 degrees, and turn AC on, comes back, and then we get another 99 degrees. It says turn AC on. We get another 99 degrees. It says turn AC on. It gets another 99 degrees. And we say turn AC on. What's the problem there? If we don't have an acknowledgement, if we don't have an ACK, if we don't have an acknowledgement of some sort, we have no idea what the hell is going on here. We could be sending data, and the database is screwed up, something got corrupted or whatever else. So even though the data gets sent, that should trigger the air conditioning to turn on, right? There should be a relay. There's a relay connected to this device to turn on the AC. If something's corrupted in the database or whatever else, maybe that's a problem. Or maybe, it's getting the thing, it's trying to turn on the AC, but it's not turning on for some reason. The circuit breaker failed or something like that, right? One of the things you need to be thinking about is how can you send an acknowledgement back to your server to say whatever has occurred, right? It is 99 degrees. You send turn on AC, and then basically sending some kind of JSON response back. You can say, turn on AC received, turned on, digital pin 1, blah, blah, blah. And that goes back. And so that will be, I'm acknowledging I received your command, and the action that I took is this, and this is happening. All right. If there's some kind of electronic mechanisms within the AC, maybe you can have something that'll actually state that the AC has been turned on or has not been turned on. And so one of the things you need to be thinking about is there any kind of acknowledgement in the system that you're creating to state, one, the device actually got the command that it was supposed to get, and then two, does that have information so that you can figure out what the hell's going on when you're trying to troubleshoot? Again, if you have a server room that's overheating 1,000 miles away, is it good enough to simply say turn on the AC? Do you need additional information to go along with that? Again, if you have a whole bunch of different devices, what additional information to do that acknowledgement? So you send, so basically the device asks for information, it gets that, it's that pull request, gets the information, and then it actually just simply does a push to say this is what's going on. And maybe there you also do an acknowledgement, and then you also got to think about how many acknowledgements you want to make. Hey, I need information. Okay, I got the information. Thank you for telling me you got the information. No problem. No, I don't mind telling you I got the information. No, it was really nice of you that I got the information. No, really, right? Again, that's the other kind of thing. How many acknowledgements do you want? That's some of the stuff that you have to think about. But anyways, acknowledgements is an important thing with this whole push, pull, and polling system. And so there you go. You learned some about push, pull, and polling in systems architecture. Or you got a good nap. One of those things occurred because there's no acknowledgement system here. See, I am pushing data towards you, and I have no idea what's happening once that data gets to you. You might be snoring away. But anyways, it's really important to be thinking about this type of thing because again, as we go in the main channel, so if you go to the main Eli the Computer Guy channel, you're seeing I am focusing more and more on projects. Again, my main focus for 2024 is I've seen so many technology professionals, especially with AI and quantum computing and IoT and robots and things, They like to talk. It's weird. You'll sit there and you'll be talking with people about how AI is going to take over the world. And then you're like, oh, how are you deploying AI? How are you scaling AI? What are you actually doing with AI? It's like, oh, that's not the point. That's not the point. And so one of the things I'm trying to do with the main channel is start focusing on actually building projects that either solve real world problems or simulate solving real world problems with a lot of this new technology. Again, whether it's AI, whether it's quantum computing, again, the robots, the Lewis Rossman tracking robot, all of this kind of stuff to really show you how this stuff works and give you ideas for how you might be able to implement this stuff into your own organization. Again, one of my big frustrations, I've been doing technology since 1996, way too close to 30 years at this point. And honestly, one of my big frustrations is even for technology professionals, we're still using computers the way we did in 2000. I mean, you think about it, keyboard or monitor, keyboard, mouse, printer, internet. I mean, now we have touch screens. Now we can talk to our computer a little bit. But if you really think about it, it's been 24 years. And most of us not only are maintaining systems as if it was 2000, but we're actually deploying and creating new architectures based off of it being 2000, which I think is absolutely ridiculous. And again, frustrates me. And so one of the things I want to do is with these projects is, again, create these architectures, create these systems so that you can see how all this kind of stuff works. And why this kind of thing becomes important is when you're designing your own devices, right? When you're building your own systems, you need to think about how things like this kind of communication works. When I got my MCSE back in NT4 back in 2000, one of the most frustrating things was we had to study so much crap that we were not able to modify. Right, again, you think about this NT4 proprietary systems back in 2000. We had to learn about encryption. We had to learn about communication systems. We had to learn about all this crap. But the worst part was there were no checkboxes. There were no drop-down lists. It was just how the system was built. Like, this is the encryption you got. Suck it. You don't like it, it doesn't matter, right? One of the things to be thinking about, right, as time moves on. And so as we're now out here in this world where we're building our systems in a way that we have not done in the past, and we're able to build systems in a way that we have not done in the past, been able to do in the past. We need to be start thinking about, like I say, this push-pull communication. What is the communication style between a client in Active Directory and a server in Active Directory? I don't care. Don't know, don't care. It's on the same LAN. It's fast. It works. I tippy tap type, I get the response that I'm expecting. Is it push? Don't know. Is it pull? Don't know. How often does it pull? I don't care, right? Because it's that world where it just works and doesn't matter what I think anyway. Once you start getting this IoT world with service-oriented architecture, this kind of thing, you've got divergent systems all providing, a tremendous amount of data that then has to get ingested somewhere. It might be getting ingested by multiple different systems. Those systems then have to spit out some kind of result. When they spit out some kind of result, how does that get to the next system down the line? And then with all of that, how the hell does your little IoT device that's sitting in somebody's installation truck out in the field, how does that device actually get the information? That's where all this kind of stuff actually comes in, and you need to be thinking about. And again, one of the killers is you don't think about it. Like I say, with this whole polling process, do you want to poll every second? Do you want to do a while true loop? And as fast as that while true loop works, you're going to poll your server. Right? You might end up crashing your server. Again, remember, ping of death doesn't happen anymore. You actually used to be able to crash servers by simply pinging them too many times. Well, think about it. You got some crappy Linode instance or a Linux instance up on Linode. You are literally polling. You're making requests as fast as 1,000 of your little devices can do it. You might actually end up crashing your server simply for trying to respond to all these different devices or cause weird problems. Where on the other hand, you're like, okay, well, no big deal. We'll push that out to 30 minutes or whatever it is. But then what you have to think about is the longer that time in polling, that scheduling, the longer it'll be before your devices receive communication from the servers. How do you weigh all that? That's the question. That's the question. I don't give you answers. I simply give you more questions. But I give you a lot of information when I give you more questions. So, anyways, and that's the concept for today. This is what I'm actually thinking about, and I'm working with the things that we're doing with Eli, the computer guy, the main channel. As always, I enjoyed doing this particular video, and I look forward to seeing the next one.